All right, guys, we're recording now. So. Okay, so today's lecture is going to be on atmosphere, and generally in the past I've gone into a lot of depth on these slides. Today I'm going to try to go through them a little bit more quickly, and then we're going to spend more time on the painting and how do you implement process. So there are three different ways that atmosphere reacts to light, or I guess not all of these are reactions, but first one is emitting light. Sometimes atmospheric stuff at a high energy will actually create light. You also have scattering of light. So, you know, this is a great example of just a cloud that's almost completely white as the light is passing through it, especially on the projector. And then blocking or absorbing light. So we're going to talk about each of these, and the last two, the difference is going to be based on a couple of different factors. So particle size and the density of the atmospheric effect are going to be the biggest issues. So just as a general principle, atmosphere lowers the contrast of distant objects, and it's going to affect shadows more than highlights. And so if you have, say, a mountain, you will take the brightest parts of the mountain down in brightness a little bit, but you're going to increase the brightness of the shadows quite a bit more. And this, I think a lot of it is just because the scattering or the particles that are in the air are bouncing light back to your eye. And so some of the light that's coming from the mountain is coming and being bounced away by those particles. That's why they get darker. But mostly what's happening is the particles that are in the air are actually being brightened by the light, and that's what causes those shadows to increase in value. And so here's a great example of that. Very low contrast deep backgrounds, higher contrast foreground, and very high contrast closer foreground. This is Bierstadt. This is Marcello Vignali, and you can see, even though this is not necessarily a situation where there would be a lot of contrast, I mean, where there would be a lot of atmosphere, he uses atmospheric principles to help express the idea that there's depth. So if for your assignment you're doing an interior or even a closed space, you can still use atmosphere to help communicate. You can see even just here on these checkers the difference from front to back. My apologies for the coughing, still not over the cold that I got last week completely. I also really like, you know, just simple things like these rafters. Such a great depth being expressed just by slight changes in that contrast there. This one's just a little bit more subtle, but you can still see it. You know, we have the darks on this foreground thing are much darker. The lights are lighter than the stuff that's happening down here. So we're going to talk about a couple of different specific kinds of scattering of light that happen because of atmosphere. Rayleigh scattering is probably the most common one we're going to see. And this is when you have binary molecules, and they have because they're polarized and because of some other things, I'm not going to explain all the physics behind it, but basically what happens is the lights, any bright light, well, really any light, but the bright light is where you're going to see this, hits that molecule, the red light is going to have a tendency to pass through, and the blue light has a high probability of being scattered to the sides. And so this explains the reason why the sun is red at sunsets. It explains why the sky is blue. And you can see even here there's an example of the moon. As it gets near the horizon, will actually get redder, because as the light is passing through that atmosphere, that blue gets scattered away, and all that's left is the reds. And you can also see this on basically any white object. If it's white and it's being lit by the sun, it will do basically the same thing. As that thing gets farther into the distance, it's going to get redder or yellower or whatever, depending on how far away it is. And you can see that here. It's probably a little bit harder to see on the projector, but we have a pretty pure white here. And then as we get back here a little bit, it's starting to get a little touch of yellow there. And then you can see how it's getting not only darker, but actually warmer in temperature in those whites, right? But the opposite thing is happening in the shadows. We have these kind of cool shadows, but they're mostly kind of these cool grays. And as they go back, it's actually getting more and more blue. And there's quite a bit of contrast between the bottom and the top here. Back here, there's getting much less contrast, and to the point where here you can hardly even see the shadow stuff back in that distance.
Is that at any time of day?
This is at any time of day. You can see here on the snow in the mountains, white in the foreground, yellower as it goes back. Because usually the clouds in the mountains, because they're low to the earth, they have a tendency to disappear around the curve of the earth before they turn the red that, because if you think of it like this thin layer of molecules that make up our atmosphere, that, the sun is actually passing through quite a bit to get to our eyes when it's coming in at an angle. Whereas a mountain is, much, much closer, doesn't have to go through nearly as much. And so that's why you have the more pronounced effect with the sun and the moon than you would with the mountains. So we'll talk a little bit about clouds. Not a whole lot about them, but most clouds are made of little tiny particles that cause a type of scattering called Meas scattering. And it basically just scatters that light perfectly. It scatters it as white light. But as those particles increase the amount of water that's in the particle, then it gets larger. And the larger particle has even though it's still white-ish, it absorbs just a little bit more of that white. And so when you get those in a large volume, you actually get gray clouds. And you can see on this image, we have these bright, bright white clouds, and then in front of them, these kind of grayish clouds. And the distribution of these particles, I've seen a whole bunch of different things, just kind of like random, one arm of the cloud gets dark type of thing. But the most common that I've seen is where the particles around the exterior of the cloud are darker. And this creates something that's similar to the fuzz effect that we talked about earlier, where you see the white in the center and then it gets slightly darker around the outer edges. I've also seen this quite a bit where it's white up at the top and gets darker down at the bottom. I don't know if I have an example of that. You can kind of see it here. So lots of white here, then a bit of the grayer color, and maybe even a little bit of that gray up here. Hard to tell because how much of that is in shadow. But because of that, clouds have this really interesting way, that darkening that happens. You can see it right here. When you get some of those particles kind of distributed around the outside, you end up with this kind of darkening. It almost looks fake when you're thinking of it in traditional, in the sense of like traditional lighting. And you just have to remember that darkening that's happening there and there is because of particles. Because the particles are getting larger.
Hey, Sam?
Yes?
Isn't this such a complicated thing that you really just want reference the clouds, right?
So the question is this a thing that's so complicated that you would always want reference? You can paint it without reference. If you understand the principles, you can actually make this happen. And I'll try and do a demonstration on how you would decide where to distribute the lights and darks and stuff. We'll do that toward the end. Another thing to pay attention to in when creating atmosphere is, depending on the situation, you may actually have other particles in the air. Let's just talk about what happens when you've got a lot of fluctuations in temperature or in air pressure. Does anybody know what a convection current is?
So it
At
flows
At
from
one
hot to
point,
cold,
I knew.
right? It's like the flow of energy from heat to cold.
Yeah, so you've got a region that's hot and you've got a region that's cold. And in the larger atmosphere, sometimes you'll have a cooler area and a warmer area that will flow into each other horizontally. But most of the time, convection currents happen vertically. So what happens is that your particles, ideally, they want to be like this. So the cool particles, they contract, they get heavier, they want to drop. The hotter particles expand, they want to lift up, right? And so if you have ever a situation like this where you have the warmer underneath the cooler, they're going to try and find a way to move past each other. But because there's this medium, this solid distribution of those particles in the two places, they can't just filter past each other perfectly. What happens is that they end up moving in these kind of flows. You'll get this section that will move up, and while this one's moving up, the sections around it will move down. And what that results in when you have that happening all around is you get these kind of circular currents that sweep past each other, kind of twist and pull, and the warm is going up to the cool, and the cool is going down to the warm in these kind of circular patterns. So this is a useful thing to know because this is going to affect how you do clouds, it's going to affect how you do explosions, it's going to affect how you do fire, it's going to affect certain things with respect to water. This is how things move when you have two fluids moving against each other. And in clouds, the way that expresses itself is you get these kind of round-shaped cells of convection that are the shape is displayed clearly in the cloud of these rolling, turning, moving convection currents. So instead of just showing you all these pictures that show this, I'm going to show you a time lapse that I took outside my house. This was taking a picture once every, I think it was 4 seconds, right? And it's surprising how fast the clouds move. And you can see how, I know this is just kind of a grainy animated GIF, but you can see how these giant cells, they're moving outward. It looks like an explosion, right? Like this is an explosion in slow motion. So you have the inner part of these convection cells moving upward and the outer part moving downward. See that? How it's rolling.
Is that a convection current of the cloud itself, or like the air around
So
the
is the
clouds?
current always up in the center of that big shape, and so just like spills out over the outside? Like
So
the current is going on.
there are multiple convection cells here, right? That you're seeing. You're seeing the larger bulge of it as it's moving upward, but you're also seeing within it these smaller ones that are turning and rotating in themselves. And it's a little bit hard to see those, how these individual ones are moving. If you look at this really close, you can kind of see how these are twisting, and the outer edges of them are pulling, as opposed to the interior sections. It's really, it's very alive, the way that it moves. Like one convection cell doesn't stay constant up through the whole thing. Like this one will die out, and this other one will kind of take its place and stuff like that. So you can kind of get into your arm, into your way of thinking how this movement is happening. And your clouds are going to be much more interesting. They're going to get this energy to them that goes beyond just, here's the fluff, right? You're actually like projecting energy as it moves, because these things are, this is explosion that's moving.
What makes the cloud flat on the bottom?
What's that?
What makes the cloud flat on the bottom?
I don't know exactly. I know I learned at one point, and it was just one of those things that wasn't really that useful to know, so my brain discarded it. Maybe if you're a meteorologist, it would matter, but I think that's a good thing to remember. Clouds are flat on bottom most of the time. They aren't always, so it's not an always rule, but the way that they do flatten out in the bottom is good to remember, though, that they don't just drop off and then flatten out. There's kind of a rounded thing that's happening right at the bottom there. And you'll also notice that it doesn't stay light, even though the light in this situation, it was behind me. So you can see where the gray parts of the cloud are, right? And you can see even gray parts of the cloud up here, kind of those outer edges that I was talking about. But you'll notice there's actually a graying that's happening towards the bottom. So most of the time with these flat bottom clouds, there's a little bit of graying that happens as it turns onto that under edge. So if you light it like you would something traditionally, you would keep it light and then round it off. So with a cloud, there's actually a gradient going up in gray up from that bottom part.
So would that be because like the particles are like the water particles are bigger and so they're going to the bottom of the cloud, or?
That would be my guess. I'm not a meteorologist, so like I said, I've seen different distributions of this. I've observed them. I don't know why the distributions happen the way that they do, but your guess is as good as mine on that. So I also just wanted to point out these little fluffy bits that break out. Like you can see how that part splits apart. It almost is like a flame that curls off and dies out in its little individual parts. So that's going to be another useful form, another type of energy you're going to want to communicate. So think in terms of rhythm when you're doing this stuff. And you get this, when the winds get really turbulent, what happens is the cloud kind of breaks apart, it kind of rips it apart, and those little bits follow around the outer corners and edges of these convection currents. And so that's where you end up with this kind of like wispy stuff that is breaking apart. And you can see lots of little bits in this picture where that's happening. And like I said, this part looks like an explosion, this part looks like a flame. These are the same ideas, the same forms that are, they're being just rendered in different ways. But when you get to flame, it's going to follow all the same principles. So you can see the exact same types of forms happening. It may be just a little bit more violent. There's a little bit more turbulence in those forms. It's not as like fluffy and round, right? But this little spout that's happening off to the side, that looks just like the thing on the cloud that was breaking off and coming out, right? And I will post that image on the blog so that you can, the animated GIF. Hopefully Blogger will take it, it's pretty big, so that you can study that stuff a bit more. One thing I just wanted to point out in this is that there is another factor that happens with flame where it's cooling down as it moves up and outward. And so the inner parts of these flames are hot, and any place where it kind of gets separated from that main source of the heat, it starts to darken. But as it darkens, it gets redder. So it starts at the yellow oranges, rolls into the reds before it goes into the grays. And so, yeah, up here it's quite a bit darker, a lot more of the reds, and it splits off and turns into the smoke eventually. Trying to think if there's anything else to point out about this. I think that there's a lot of stuff that I'm never thinking about when I'm doing explosions, but I think it's worth paying attention to. So see how the flames here on this part of the explosion, they almost have this arc-like thing going on. It's almost like the same form that the cloud bulbs, or what, I'm not a meteorologist, so I'm sure I'm calling everything the wrong names, but they're coming out in these kind of bulges, but there's these really intense strands stretched across it, right? Just where the heat is really concentrated, it gets really these really like strong, interesting shapes kind of carved into that larger part. So we talked about this stuff already. Here's a great example of what I was talking about. Just, this part is being lit by the sky up above. And there's all the dark parts are on top. So, and that's not going to happen unless you actually have something darker around that's kind of shaping that cloud. And because these are separated like the fuzz would be, when you look into the center of it, you're seeing the white underneath, and around the outer edges, you're seeing the darker particles.
But it's being lit from like just like all angles, kind of like this atmospheric light.
Well, the sky is a gigantic fill light, right? And the center of the fill light is going to be the most intense part of the light. So if we go by that,
So does the fuzz effect work with like according to where your eye is or where the light is?
it doesn't matter where you are. It'll be the same because it's a Lambert reflection. With any type of scattering, you get Lambert-like reflections in that they are uniform. They're always responding the same way no matter where you are, instead of being different depending on your viewpoint. Does that make sense? So anyway, and you can kind of see like here, this part is being lit more traditionally. You don't get the kind of darkened top. There's another thing that's happening on this cloud though, which you definitely need to pay attention to with clouds. They have a ton of subsurface scattering. If you have a giant fluffy cloud and the sun is hitting it at any point, that just filters through almost the rest of the cloud. And it's not reaching clear over here, but you can definitely see it up here, all that light that's filtering through. And also because of the subsurface scattering, the bottom can get pretty dark, but there's never these quick transitions. It's this very long gradient from the top to the bottom. Another example of that subsurface scattering here. You can see the places where the sun is striking it directly, and then you see all this light kind of passing through on the underside of it. And we'll paint in just a minute just to show you how to achieve that effect. So let's just talk quickly about Tyndall scattering. Tyndall scattering, it's similar to Rayleigh scattering because it allows reds to pass through and blues to are scattered out to the sides. It's not quite as strong as Rayleigh scattering. It's kind of a soft effect, but usually the way that it shows up is when it's like particles that are spread out. So like if you poured a cup of milk into like a large puddle, it would turn blue, just slightly blue, because of Tyndall scattering. But the milk is not blue before you pour it in. It becomes that when you pour it in, right? In fact, skim milk, because they've taken out the fat particles and you're just left with these smaller particles suspended in this greater medium, it has a little bit of a blue tinge to it. So that's why skim milk has that blue edge to it. And you'll also see Tyndall scattering in smoke. So smoke, generally when you've got like a big mass of it, it doesn't have that blue bit to it, but on the edges where it's starting to dissipate a little bit, it gets a little bit of a blue edge to it. Unless you're standing behind the cloud and the sun is that way, and then it looks red, just like Rayleigh scattering. And I don't know if these are the best photos, but you can kind of see a little bit of that blueness in both of them. Yes?
You kind of lost me
On Tyndall scattering?
Yeah.
Okay.
I'm lost with her.
All right, we'll show that in the example also. So what I'll do is I'll paint a cloud and then I'll paint smoke and show you the difference. Okay.
Sounds great.
And I think that's all for the technical aspect. So the great thing about atmosphere is that it's extremely expressive. That happy, fluffy clouds bring happy, fluffy thoughts into your scene, and dark, brooding clouds bring dark, brooding thoughts, and swoopy, unnatural-looking clouds bring a feeling of mysticism. I mean, it's incredibly expressive. And, I mean, you could see the difference even in just these few. Like, there's maybe like a tiny, tiny little bit of hint of moodiness to this one, but it's mostly just kind of fluffy and nice, right? The clouds make it feel kind of soft and approachable. In this one, not so fluffy and nice anymore, right? And the fact that the clouds are absorbing so much of that light. And even in this one where you get a mixture of both, you get this kind of, I don't know, nuanced feeling about the scene. Like it feels happy and you know, you kind of get this like nostalgic feeling, but there's this like element of darkness and element of unsurety to it. And I think you can use that in your scenes when you're trying to create something like that, you know, that has multiple layers of feeling to it. Also, you can use them to center the composition or to control the composition of your image. So, you know, that giant tower, the clouds just pull you completely around it. You know, they create a frame, and it's mostly an implied frame. Just that single arc kind of creates this mental circle, and, you know, it's effective. Even though this is the highest contrast part of the image, your eye is drawn naturally up to there because of the arrangement of the clouds. I don't think the clouds are different than other things for that, but I think often people will forget that the clouds are a compositional element and should be used as such. Fog has a tendency to add moodiness and drama. I don't know if I've ever seen a happy fog. So, you know, even in this one, I think some of the sense of drama and tension to this comes from the fact that the clouds are pulled down onto the mountain, and it adds that kind of slight fogginess, mistiness to it. So just be aware of that. Like the foggier you get it, the more it creates a sense of mystery and tension, because you want to know what's out there. You want to know what this character is all about, but you can't, right? Sometimes people call these God rays when you have a beam of light that is passing down and catching on the atmosphere. In a clear atmosphere that is, you know, mostly you're just getting nitrogen and oxygen, which is what gives you Rayleigh scattering, then you will have different colors of beams. If you're looking at the beam from this direction and it's coming down up and down, right, and you're perpendicular to it, it's going to be blue, just like the sky is blue when the sun's over there and you're looking up at it, right? But if you are looking at the ray that direction and it's coming toward you, it's going to be a warmer color. And that's why you end up getting, in this case, a blue, and in this case, a warmer color. It has to do with the angle of the sun with respect to the viewer. However, a lot of the time, the reason that you'll get God rays, and the reason why you don't just get them at any time, is because there's other stuff in the air, and that will change the color. So if you just have like a very cloudy sky and just one little patch, and the sky is clear, I mean in the sense that like there isn't gunk in the air, then you'll end up getting this blue thing, you know, versus the golden thing. But in a lot of other cases when you get this, it's because there's dust in the air, other stuff like that. And in that case, there isn't the color shift. It's just going to be kind of this warmish gray, warmish color, depending on the color of the sun at that time of day.
Even if it's going straight up and down, you're looking at it straight on?
If it's made from dust or because it's humid or something like that, then it'll be the same color kind of no matter what.
Well, that's because the sun is like bouncing all over the purple and it makes it warmer. Kind of like a cooling shadow.
Yeah, it's because the sun is a warm light source. So if you had a really strong blue spotlight, then yeah, you'd end up having it be blue instead. It's more that the particles that are in the air kind of neutral colored, and they're responding to the fact that the sun is warm and that the sky and clouds around it will be cool. Why you do that. There's something else I was going to say about that. Oh, so dust. If you have God rays that are caused by dust, what happens with that dust is going to be different depending on your angle. So dust, in most cases that I've observed anyway, I don't know if it's just because most of it is skin, and skin has a tendency to be slightly specular. This is going to gross you guys out, but so if you are there'll be times when you have a beam of light coming in through a window and there's no beam of light. You don't see the dust, right? But if you align yourself almost with that beam, then it'll show up. The dust will actually be showing there. And that is a specular effect that happens because of the Fresnel effect. So the Fresnel effect means that if you're getting to be parallel with the surface and the light source so that you're almost lined up, you get higher specularity. So dust will disappear as you back away as you get closer. In fact, I would be willing to bet. Yep. So if you're curious about this effect, come walk up here and stand right next to the projector and then take a step away. The dust completely disappears if you step very far away. And yet if you stand right next to the beam, then it becomes really strong.
So is that kind of like a rim light on the
Yeah,
particles?
yeah, it's kind of like a rim light. But yeah, it's more like if it was just a rim light, if it was just that they were all being illuminated the same, then you would see them right now. It's the fact that they have a specular reflection that you can only see it from a certain angle.
So if it's just dust, why is it like specular? Why is it so?
I don't know, but I think it's mostly skin.
Skin flakes.
Yep, skin flakes.
Oh, lovely.
They're all over in the air all the time. You can't escape it. If you're grossed out by that sort of thing, you better get used to it because your entire life is going to be spent around floating skin particles.
Just stop breathing.
Hey Sam,
Yeah.
whose painting is in the middle of the top? Is that
This one?
just below that one?
Oh, that's Craig Mullins, I believe. Yeah, I haven't been listing off the names of all these. I believe that is Craig Elliott. Yep, that looks like it. Craig Elliott. That's Craig Mullins. I forgot who did that. That's one of the Hudson River Valley painters. I forget which one. It's not Bierstadt. Don't remember who that is. That is Jing Zhuangji, or however you say his name, the Chinese guy that's really cool and unpronounceable. This is George Hull, I believe. Let's see. Yep, that's George Hull. I think that's Bierstadt, Bruce Zick, and someone. Okay, so like I said, adding fog adds mood, but you can instead of doing a uniformly distributed fog, you can take that and just squish it down to somewhere. If it's messing with your composition, if you want to be able to see a distant object, but you still want the moodiness that fog adds, just take the fog and drop it down to the ground, make it focused. And these don't look great up on the projector, but you know, this is an incredibly moody piece. The fog is very localized. It has a tendency to add a different type of mood, where you know this one obscures things and adds an element of mystery that is, you know, you want to know who's standing there and you can't type of thing. This, you do see what you're seeing, and I don't know if it's just like a psychological association thing or what, but it almost adds like a mystical element to it, maybe because it's not something that we see all the time. And don't forget other particles that can create atmosphere, you know, like surf being tossed up in the air, other things thrown by the wind, machine gun shells, fire, spit. I'm trying to remember.
Dinosaur skin.
Dinosaur skin, yes. Also specular. Anyway, yeah, so you can, when you put that type of particle in, the like actual big chunk stuff tossed in the air, it adds a lot of energy. If you want to create energy in your piece that is very kinetic, toss stuff up into the air, even if you're just saying it's being caused by a wind or something that just happened. I think that's how you pull that element in if you need it.